My name is Chris, for those who don't know, and I'm the chair of the Adelaide branch. We have a great presentation today from Karl Spandler from the Adelaide Uni and from one of our up-and-coming students, Ben Forrest, who's currently studying geophysics. But before the presentations, I'd like to just run through a couple of announcements, if I may. Bring the slide first. There you go, went the wrong way. All right. Look, firstly, please ensure that you're all following social distancing requirements and any instructions given by staff here today. And for those who have not completed your contact details at the front desk there, we need those as a requirement from the delivery guide. So please ensure that you put your phone numbers on the list. I'd also like to acknowledge our partners for 2020. It's always great to have them on board, and as much as we've been trying to plug them over the last few months, it's great to actually have them here in the room with us, and also be able to sponsor them, promote them on the big screen. So I'd like to first thank one of our long-standing partners, which is BP. They've been with us for quite some time, and it's always great to have them here. Also, Oz Minerals, a big thank you to both of our French partners. We've got Oz people here. There's Oz. There we go. And BB guys, BB guys. Oh, there we go. Excellent. All right. Big plug to both of our branch partners for 2020. I'd also like to acknowledge our technical lunch partner, Stella. Big thank you to them. They've been partnering with our technical lunches for some time too, so it's great having them on board. And also finally to acknowledge Engage, who are our 2020 media partners. I don't know if we've got anybody from Engage here, but we will acknowledge them in their absence. And it's thanks to all of our partners, both branch and the technical partners, that we're able to continue our loyalty card in 2020. So if you haven't got your stamp today, please do so. But please remember that complimentary don't count as a stamp. But you come for 5 and 6 want to go on us. And a very quick point for our next technical lunch, which will be here at the pavilion. And that will be with Geology of the Carolina operations. This is an event that should not be missed. But please, the registration board is now open. We need to know the numbers sooner rather than later so we can work out are we going to be in this room or we're going to be in the bigger room. So please register as quickly as you can for that so that we can organise the event in August. I'd also like to announce our annual dinner, albeit a little bit late, is coming up later on in September. And with our special guest speaker, Dr. Russell Payne, who's, where is he? There he is. Yeah, hello. All right. He will be providing the entertainment for the evening. But in addition to that, it will be a fun-packed evening with lots of awards, presentations, prizes, and a chance to catch up with your friends in a socially distanced environment. So anyway, that's now available for booking, so please go and check out the Geochronology webpage for booking details on that. Another one of save the date, we're pleased to announce the 46th Essington Lewis Memorial Lecture will be given this year by the Honourable Christopher Pine. Further details will be announced on this one shortly, so keep an eye out for that. And another save the date, this year we're moving away from the rowing club for our AGM and we're going to the bowling club in the city. This will be a free event for members, and again, we'll be posting the details on registration very shortly. Now, this is one for the students. I'm pleased to announce the prestigious EEF, Adelaide's own Playford Trust, and the FEROC scholarships are either open or about to open. So it's a fantastic opportunity to kickstart your career, and I encourage all the students to go and check out the webpage for further details, and to please get the message across to all the students that these scholarships are now open. All right, the last thing is the door prize. I've got the tickets, but I need someone to draw a lucky number. Do we have a 55 in the room? F55. Hey, right, okay, all right. We'll be able to grab the details shortly, so stay put. All right, cool. All right, that's about it from me. So what we'll do now is we'll move on to our first presentation for today. The Adelaide branch currently works with high achieving students, providing scholarships and mentoring programs. Ben Forrest is in his final year at the Adelaide Uni, studying geophysics and looking at tectonic plate reconstructions. Ben was awarded a major scholarship with Glencore and will start an internship with them after graduating once he graduates. And here at the Adelaide branch, we have been able to include Ben in our local mentoring program, which comes with the opportunity to do presentations at our events on final-year projects or other significant work at events like this. So, without further ado, I'd like to invite Ben up to the stage. Ben's presentation today is on tracking weights in sub-level cave operations using geochemistry. So please welcome Ben to the stage.
All right.
Thanks, Chris. So good afternoon, everybody. My name is Ben Forrest, and today I'll be briefly talking about the project that I did while on vacation work at MS Henry, which is a copper gold deposit near the town of Cloncarry in the northwest Queensland. It's one of the world's most efficient sub-level cave operations. So I've just included in the image here for those who aren't really familiar with sub-level cave, I'm sure most of you are. Basically, there are sub-levels that go through the ore and multiple ore drives on those sub-levels. And up here, you have the production levels and the development levels, which we mine later. And material is blasted in rings and so we retreat back that way with the ore. And waste material from above collapses in, and once the ore is extracted from the draw point, and that forms the cave here. So just to give you a quick background of the MS Henry deposit, it was originally open pit, started in the 90s, but then it's now fully transitioned into a sub-level cave since 2015. In December 2015, the resource was at 87 megatons of almost 1.2% copper grade and 0.6 grams per tonne of gold. And its current life of mine is 2027, but that could change. So geologically, this is a branch shear pipe IOCG deposit, which basically means it has the shape of a cigar underground and it dips moderately to the south, so you can kind of see this here. And this geometry is what makes it so ideal to be mined as a sub-level cave. So the ore shell, as you can see here in red, is surrounded by various different waste pipes. But an important one I'm going to touch on today is this waste pipe here, which is known as the interlens, and it basically cuts the ore body in half at depth in the deposit. So getting into my project, so the technical services team, which includes geology, were facing an issue when I arrived, where in some cases waste would show up at draw points earlier than planned, which meant that there was dilution occurring somewhere up in the cave. So my project basically was just to identify what waste types were showing up early and what their origin was. So this helped this aim to improve this one. So basically I was going to grab samples from draw points while I was going on underground trips with the geologists every day for inspections. So this diagram here is just one of the production levels, and the stars just show where I collected some of my samples. So tried to spatially space them out where I collected them. And this kind of just shows where the influence is. So you've got the main ore body here and another part over here, which is divided by this influence, which is kind of shown here in 3D. Overall, I collected over 50 samples. So basically the idea was to use geochemistry to see if we could accurately determine which samples I grabbed were interlands because different waste types have different elemental compositions. So to do that, I had to also use some drill core, because basically with drill core you know exactly where it's come from in the deposit, its origin is certain, but material that's been in the cave or has been involved, there's some uncertainty in what its origin was. So the idea was to compare the known samples to the samples that I collected. So once I collected all my samples, I had them crushed on site, and then I used this XRF gun just to scan the chemistries, so the full element compositions and their concentrations. So basically here are the results. So the blue, orange and grey lines are samples that I collected that had similar chemistries, and the yellow line is the drill core, so that's kind of like a control variable what we're comparing against. So I basically want to see which group of samples match the yellow line the best. Good. So basically, some of these peaks you see are due to the common minerals in the deposit. So iron is due to magnetite, which is everywhere. It's in ore, and all waste types alike. Silica is found in waste with quartz and other silica minerals, and so on. So, but to get a more detailed picture, I kind of had to put these elements to the side because, like I said, they're found everywhere and they don't really tell us much. So we want to look at more of the trace elements, which are more likely to tell us something. So just ignoring those. So you can see the grey line matches best to this yellow line of the drill core. So these grey samples are probably more likely coming from the insulin zone in mine. Especially for elements like aluminium, titanium, and manganese. So these must then be important elements which can tell us whether the waste is from the insulin zone or not. Also, we can see there's a peak for this blue group of samples that I collected, and that's probably likely telling us that this waste type has come from an area of the mine and the hanging wall. And finally, just looking a bit closer, these two elements, yttrium and zirconium, were also pretty good at indicating whether waste was insulin or not. So basically, I just concluded my project by presenting my findings to the team there at Ernst & Henry, and I kind of suggested that this was probably a good method for them to use if they wanted to quickly determine where waste was coming from, because they can not only use it for insulin but for other waste regions in the mine. So it's a quick and easy process, and it's kind of better than looking at just minerals, because some waste types might have similar mineralogy but different trace element compositions. So my findings kind of have big implications for our operation, because, for example, one sample I collected here at this drill point was definitely insulin waste, and so it kind of suggests that it will come from over here somewhere, which suggested a lateral flow in the cave, which isn't really like the flow model sort of accounts for more vertical flow rather than lateral flow. So the flow model might need to be sort of considered for lateral flow as well. And I just summarise by encouraging the geology team to maybe continue this approach in order to work out quickly what was happening in the cave, especially as they continue deeper into the deposit. Yeah, so thanks for listening. I'd like to thank the technical services team, especially the geology team at Ernst & Henry, for allowing me to do this project and allowing me to present this today. And I'd like to thank Oslo and Adelaide branch for allowing me to present. Thank you.
Before I let Ben go back to finish his meal, if he hasn't already, do we have any questions for Ben before he... Oh, on the floor, yes.
My question is about your methodology. XRF gun, of course, takes a minute point as a sample. And how does that compare then, of course, with a normal geochemical sample you would take where you, say, 2 or 3 kilograms crushing and blend it, and you've got a blended sample where you take an alcohol. So how did you actually tackle that issue?
Yeah, so the crushing did actually, so it was taking the bulk composition of the rocks, and while I was collecting samples, I made sure that I was collecting multiple samples from across the draw point at different logging tonnages. So I was trying to make those samples as representative as I could. And like I said, the sample was well mixed, and so when you scan it, it's pretty much telling you about bulk chemistry. Yeah, if that answers the question.
The XRF gives you an indication as to samples which may be interesting to look at in the lab at that stage.
Yes.
Is that all right?
Thanks very much.
Any more questions? Otherwise, thank Ben for his presentation. Again, thank you, Ben. Look, on to our main presentation today is with Dr. Karl Spandler. Karl completed his PhD at the ANU before moving to the University of Bern in Switzerland. More recently, he was at the James Cook University from 2008, before being appointed to the University of Adelaide this year under the Top Talent Initiative. He has been leading and developing research in critical mineral exploration, particularly those elements which are crucial to the transition to a renewable energy future. Today, this talk continues this theme with a review of the geology and tectonic setting of Australia's hard rock REE resources. So without further ado, please welcome Karl.
Thanks a lot, Chris, for the introduction, and thanks for the invite to Mark and Geochronology for having me here today. It's really good to actually talk to people rather than a screen. And it's great to see there's so many more Ironman events coming up. Hopefully, as Chris said, I recently moved to Adelaide as part of the initiative, with new research initiative the university is taking on to look at critical minerals from their geology point of view, but also through to processing, with an aim to seeing Australia can be more of a important player in this space globally. So a lot of what I'm going to talk about today is work that has been done since I was at JSU the last 10 years, and that's why JSU and Ed grew up here, because that's where I was previously. That's where a lot of work is done, but this is continuing, and will be hopefully lots more exciting. There's lots of people listed here, and these are all a mixture of students, PhD and honours students that have worked on this through the years, the last 10 years or so, as well as a lot of names you guys might recognise. So it's really been quite a large team of people working on this. It's a very big topic to talk about geology of Australian rare earth. Well, it's actually not that many overall, and I'm not going to talk about all of them. I'm just going to cherry pick a few to get some basic messages about their broad features, their large-scale features, and how they may be used for exploration. So currently, rare earths are currently considered to be the most critical minerals, and that's because of what they're used for, their strategic importance, and also currently because they're mostly supplied from China. And the historical reasons behind that are largely partly due to these guys here, Karl and uranium. So in a geological setting, when you concentrate rare earth elements, you also concentrate those guys. They just go together in rare earth. So rare earth ores are to some extent thorium and or uranium rich, which means they're radioactive. And then if you don't mine that, that becomes potentially a problem. For a research geologist like me, I think it's fantastic that thorium and uranium go in rare earths, because they're fantastic pathfinders for understanding the process you can use to date mineral systems. You can use to track the isotopes where metals came from, and including this guy here, samaric, is also partly radioactive in the case. So there's lots to play with here as a geochemist with these systems. All right, so the reason why China really has dominated supply in the Western world has let them is because of these guys. China has to deal with radioactive products, and the Western world has to worry about it. But that's obviously a geopolitical risk, having China being the major supplier, when a lot of our current technology and our future is going to be aligned. So what have we used before? Probably most people are aware of this. They're very widespread in everyday technological devices like phones, computers, all of they're used in luminescence, so they're used to make displays, colours in the displays on TVs. They're used in medical imaging, they're used mostly for, particularly neodymium, to make very high power magnets, so they're used in speakers, lasers, this is serum used for polishing glass, lots and lots and lots of a lot of now everyday applications, so very widespread throughout society, but most importantly, they're really important if we're going to transition to a renewable energy future, or things like these guys, wind turbines, that use hundreds of kilos of rare earths, and their wind generation is just going to increase in the next couple of decades, as well as hydro. And this guy here, this is actually a Tesla, which many of you would have seen is now the most valuable car in the world, Toyota, which is pretty remarkable considering that Tesla has never returned a profit as a company and represents a tiny fraction of the actual growth. The reason why it's so valuable is because the future, next 10 years, you can see a massive increase in electric vehicles. So by 2035, there will be more electric vehicles than petrol and diesel. And each one of these vehicles requires electric motor that contains rare earths, as well as a whole bunch of other. So demand for rare earths is going to increase rapidly, and even if we didn't have potential trade tensions with China will not be able to provide them. They're already restricting their output, and they want to so we do really need alternative supplies of rare earths. And that's the first in Australia, fill that gap. So in a geological sense, where we find rare earths, so this is from this paper Wang et al. A few years ago, where they looked at rare earth resources around the world and their geological setting. They came up with this diagram, and you can see most, a big fraction of rare earth resources here in the monazite. So these are carbonate-rich alkaline magnets. They're relatively rare in the geological record. But about half here is monazite. It's actually much more than that, because this piece here, the tailings, is actually tailings from monazite mines, so that's really monazite. And the laterite one here, this is weathered. For the most part, this is weathering or rising on top of monazite like number. So really, about 3/4 of the world's rare earths are held in monazites, these are alkaline rocks, and they're very much like rare earth rich. So that's neodymium rich, which is the one we need most of, but we also have most fine resources of. IOCGs are here, the dark blue, you can see that's a pretty big chunk, and that's mostly the we'll get on in a minute. And then we have a big piece of pie here, which is alkaline complexes, pegmatites, things like minor. That's really alkaline complexes. So that's intrusive systems in Greenland and in Canada, for example. In Australia, we have examples which are volcanic, so I'll talk about those. That piece of pie is more valuable than it looks, because those particular deposits are very rich in the heavy rare earths, which is much more valuable, much more sought after, much more critical. All right, if we look at a few other bits and pieces, alluvial places are a tiny fraction here, and mineral sands are only 2% of these mineral sands. Overall, it's not so important on a global scale, but if you take these deposits, most of these deposits, and look at their geologic environment, it tells us that almost all of them are either directly related to magnets, so alkaline magnets like monazite, alkaline complexes, or they're indirectly but still magnet related. So that by scars. So magnetic systems are really important for earth water bodies. And that's certainly true in Australia as well. So here's a map of Australia with bits and pieces of the basement geology shown as a function of age, with the major hard rock deposits and prospects shown on this. I'm not showing you the sands here. And they're colour coded according to their geological setting. So commodities here are shown in blue, alkaline or alkaline complexes, silicate complexes are in green, skarn ICGs through the middle here are in some pinky colours, and then we've got one up here, ground range, which is unequal. I'll talk a little bit more about that on later. That's a bit of the odd one out, so to speak. So Australia sort of matches that global record. You can see that they're all over the continent. They're not restricted to any one particular area. And these range from active operations like Mount Weld here, that they're currently producing neodymium. That's probably the biggest neodymium producer outside of China in the world. And Browns Range up here was operating over the pit, and then Kimberley got shut down. They're looking to restart that again pretty soon. Well, the only area operating mines. There are a few other deposits here, like well-developed projects. They're essentially at the point with other things that are really just prospecting. Ore system as well. Well, Olympic dam, which is very low grade and probably uneconomical to mine, so it's a process certainly at the moment, maybe not ever, but it is a massive concentration of rare earths, so to understand the rare earth system. Right, so what I want to do is just not to go through all of these because we don't have time. I'm just going to run through three deposits. Tungai down here in New South Wales, Yangovana, and then Browns Range. So a bit of a flavour of each of them to see what they look like. They're all very different deposits. The geology of each of these deposits is very different than the surface. What I want to really focus on is what some commonalities are between them, because that then can be useful for developing exploration. Okay, Tungai, so this is in New South Wales. So Dubbo, for those of you who don't know, is here. Dubbo is a city a few hours drive northwest of Sydney. So we're in central New South Wales, and the Tungai deposit sits down here. It's this tiny little white speck here. It's part of a trachyte body, so it's a volcanic unit. It's quite boring to look at the rock itself. And it's part of a series of different volcanic units, all these white splotches here, which are all related from Jurassic age of alpine volcanoes. This image here is a gravity image, so there's a big red blob here, which is the gravity high, which sits right underneath where all these volcanoes are growing. Okay, so this is a fairly mature project, and that little thing there, that trachyte has about 2% zirconium across the board, and very high levels of rare earths must happen. So the entire thing is ore body. Alkane resources have been working there for about a decade or more, and they've got that ready to go. When they do start mining, which if they can get miners to do it, is projected to have 70-year mine life. It's quite a big project. So the work we did here was to try and figure out how this thing became an ore body. It's a fairly standard looking trachy body, and we analysed the geochemistry and metrology of all these units to try and figure out how this thing developed. I'm not really going to show too much detail, not any detail about how that data, other than finishing this cartoon, which kind of summarises what we think is going on here, is that these rocks, these magmas were originally mantle-derived, so we're melting the mantle to make alkali salts that then pond in the crust here, large volumes of it, and over extended periods of time with crystallization, fractional crystallization, would leave this crystal residue in the crust. This is what now makes the gravity high. And the residual liquids, these alkaline residual liquids, are very good at keeping these rare metals in the metal. They don't go into crystals, so they just build up, build up, build up. And then we tap these residual liquids onto the surface to make these metals. Tungite itself, the metrology of it suggests that it probably had another level of fractionation, bonding and fractionation at shallow levels here to really get into that really high rare metal grade. And the level of fractionation we're talking about, crystallization, is in excess of 99%. So taking the starting parental magnet here, you need to crystallize it probably into 99.8% or more to get that normal, which is now rare metal grade. So that's tungite, and fractional crystallization is really key to all of these things, these magnetic systems. On a more regional scale, if we look at where tungite sits, this is, you can see in the background here, there's a blurred out image of Eastern Australia, and I've just drawn on top of here the basic geology units, the major units of New South Wales. So there's the Loch Lomond purple, this Paleozoic orogenic zone, and in green is the Gunnedah Basin, the Triassic sedimentary basin, shales and sandstones, and you see tungite sits really right on top of that boundary between these two major crustal blocks within hundreds of meters of the contact between. So that contact really represents a fundamental boundary that focused the positioning of that deposit there. You can see similar things with other deposits around the country as well. That's the surface geology. That explains what's going on the surface. But if we look deeper into the Earth, we can use, not we, I should say, other folks, including these guys from the ANU. Some years ago, geophysicists using seismic tomography to map the lithosphere's hemisphere boundary, and have done this through Eastern Australia, particularly well New South Wales. And what we're seeing here now is these colours that represent the depth to that lithosphere hemisphere boundary. In the east, you can see it's about 100 kilometres thick here, these sort of yellowy colours, and in the west, as we go into the continent, as you'd expect, it gets thicker. What's striking here is that it steps. So the boundary between the yellow and blue, you can trace this down, is basically where the lithosphere very rapidly steps from about 100 kilometres thick to 150 kilometres thick. Okay, some of you have seen recent presentations and publications from New South Australia on the lithosphere and assessed the boundary in basin hosting systems. That's further west where we're looking at a deeper step. This is sort of down to 100 kilometres. This is a shallower step here. But tungite again sits right on that step. So we have a major geological boundary at the surface and a major geological step right down to the surface. All right, I'll come back to what that might mean. I'm going to jump ahead to this guy over here now, Yangibana, which is in the Gascoyne province of Western Australia. This province here really is, it's a Proterozoic series of orogenic zones that represent very complicated and protracted suturing between the Pilbara Craton up here and the Northern Craton down here. So this is work done by a PhD student called Paul Slezak. He's finished this recently, and there's a series of papers coming out on this. This is the study area here in the middle of the Gascoyne province, and what I want to point out is this fault here, the lines are a very big major structure in the area. If you zoom in on here, here's the lines with the fault, and the Yangibana rare earths is really an ore district because all of these little names here are all deposits and prospects for rare earths. So this is being explored by Hastings Technology Metals. And they currently have a JORC resource of 20 million tonnes of about 1% rare earths. This again is light rare earths. So monazite is the main core mineral here, and these red lines here, these are ironstones. So these big ironstone ridges that stick out of the landscape, and it's basically iron oxide, iron hydroxide, plus monazite. That's all it's metals. A couple of percent monazite. And that's the ore. So Paul's job in his PhD was to look at where does this stuff come from. Down here you see all these little lines. These are all dike and silver spawns of monazite and alkaline various other alkaline weird igneous rocks. And so he studied all of these and was able to show that these ores are probably almost certainly weathered equivalents of these ferrofluorines. This whole complex, it's all related mathematically, and notice it's very close to this line of magnetic orientation, and that's where these parallels are fault. Got another major structure running through here, which is the parallel. So in the last decade or so, Geoscience Australia has also run seismic traverses across the country, which you can be aware of. And one of those seismic traverses ran just to the south here, which is fantastic because it means we can have a snapshot of what the crustal structure looks like. And that's here. So this is going from south to north, if you like. And here's where Yang Bar sits at the surface of the given creek one-type complex. That's one type complex that's associated. And here's the line to the fault, and you can trace that down in the seismic profile all the way through the crust, and it even probably offsets the motor down here. So again, we're looking at a very major and long-lived structure that is controlling the location of this system. So, a little bit on geochronology. There's a lot of data here, but the message isn't too complicated in a lot of ways. So Paul, as I said earlier, rare earth systems like thorium uranium, so it's relatively easy to date them. But the problem is it's much, much harder to know what those dates mean. And that's kind of illustrated by this diagram. So previously this was thought to be, this deposit was thought to be about 1100 years old. Work that Paul did, as well as folks down here at Curtin University, did this much more rigorously, looked at the whole series of different minerals, so the different colours here represent different minerals that were dated by various different techniques, and in context with tomography, so understand what the context of that mineral is in the rock, and to try and know what's going on. Pink here is zircon, so this is our most robust dating system. These were shown to be directly related to the alkaline system. They all come in here, ignore this guy, this is post rocks, but they all come in here about 1370. So that's the age of the formation of the alkaline complex. And then all these other dates here represent dating of more minerals like monazite and phosphate at their resetting events. So you can see the whole series of orogenic and tectonic events that affected the region after the complex form, and they serve to reset these events. So that's what they're dating. That's actually kind of useful because it means you can use rare earth deposits as monitors or recorders of tectonic events throughout Central Australia, for example, that you may not be able to get otherwise. Okay, but it also highlights that you have to be really careful about what your geochronology means. And this is not unique to Australia, this is well known by Novo as well, the biggest group. So 1370 is the age of Yang Barnett, and that age is kind of interesting because that's really not an interesting age in Western Australia. There's nothing happening in that part of the world in 1370. Right, so no active tectonics, no mantle plumes, anything like that. So Paul's story here is that what we had was this long-lived orogenic system, accreting various terrains between Pilbara and Yilgarn. Major one, the Glenberg geology, was when Yilgarn and the Pilbara and Glenberg terrain amalgamated. That involved obviously divergence and destruction of some plates through here, which with subduction you get enrichment in the mantle wedge. And that enriched mantle hung around at the base of the crust here, and then at 1370 you had some sort of far field effects, maybe some small-scale localized extension, enough to reactivate this fault, so LRF is line for the fault here, and enough to maybe cause a jog in the base of the crust, or the base of the lithosphere at least, to partially melt this enriched mantle, which is really fertile melts for rare earth deposits. And then that travels up this fault structure, that's the pathway up towards the upper crust. All right. The last deposit I'm going to talk about is this guy up here, the black sheep of the family, Browns Range. And this is a really unique deposit, not just in Australia, but globally. So it's been explored and worked to find all the minerals for the last 15 years or so, and it probably has maybe a record for a deposit going from discovery to mining, in terms of getting everything lined up and going. It's probably certainly less than a decade. It's a pretty amazing place, and these guys have done a great job to get this project going. We're right on the border here between West Australia and Northern Territory. And these stars represent the mineralisation styles. It's a particular heavy rare earth occurrence. And you can see it's spread over very large areas. The mineralisation style is very, very similar in all of these areas. So it really is a regional mineralisation style. Most of it is in this little bit here, which is blown up down here. This dome, this is known as the Browns Range Dome. It's a very remote part of the world, it's the northern Adelaide. And then now we're going to zoom in on this western part here, which is blown up over here. Each of the stars represents a deposit or prospect, the ore, and you can see most of them are sitting in this blue unit, which is said to be RM, that stands for Browns Range. So these are metamorphosed, immature sandstones and archives. And they're probably the oldest rocks in, well, I think they are the oldest rocks in Central Australia. So they're somewhere between 3.1 and 2.5 million years old, so up here. And to the west here, we've got this yellow unit, which is the Geochronology group sandstones. They're mid-Proterozoic, I guess, relatively underformed. So that thick line there represents a regional underformed surface. You can see all these deposits, they're sitting on faults, so these dashed lines or faults structures, and this unconformity surface, or they're sitting on the unconformity surface down here, right on it. And this unconformity is very gently dipping to the west. So if you project this back over here, take away erosion, all of these deposits are sitting pretty close to the unconformity surface. Other rocks here, these are all much older, so these are probably somewhere around 2 million years old. These may be ultra-mafic bodies, but they're not really important. All right. What does the ore look like? So it's very unusual, very nice to look at. So it's the breccia zones that sit on these faults, particularly when you have fault intersections. It's very steep dipping, and it goes from a very chaotic breccia in the centre, and as you move out into the country rock, it goes out into these mosaic and crackle breccias like this one on the top here. The main ore mineral here is xenotime. It's a heavy rare earth phosphate. It's a very heavy rare earth rich, which is why it's so valuable. Really important for dysprosium. And this is what the ore looks like. And all this pink stuff here is all xenotime. So the main ore mineral is pink here. This is high grade breccia here. These pebbles here are the altered sandstone posts. And you can see all of that here. So these are veins, crackle veins here. This is xenotime with a core of quartz. And that's almost all there is. This is also this mineral fluorine site, which takes the light rare earths. So mineralogically very simple, which is very unusual for rare earth. Usually very, very complicated mineralogy. And it's very clearly hydrothermal. The dates again, so another PhD student worked on this, Timon Zari, also did a fantastic job on it. He's now postdoc in South Africa. And he did a bunch of dating. Xenotime is a really good mineral to date, so you can directly date the ore. And these are various different samples of the ore here from various different prospects. And the primary ore is these ones in blue and red. You can see their age, they come out between about 1.6 and 1.65 million years ago, and that's across the Browns Range and these other areas as well. There's a little bit of resetting going on in these guys. All right, in terms of how you make this mineralization style, when I went there, my goal was to find the magnet that produced this ore body, because alkaline magnet is always associated with rare earths. So we really looked, we dated lots and lots of these rocks that are all older than this. Regional metamorphism is much older than this. Again, you see, as similar story to the last two cases, there's nothing going on at 1.6 in this part of the world at the time. So this is the North Australia craton largely assembled. Here's where Browns Range was at 1.6 million years ago. The only things going on was maybe the isotopes was starting up, and we had a collision down here, rocky terrain, southern end of the craton. Miles and miles, hundreds of miles, thousands of miles from where Brown's Range is. There's nothing going on. So no magnetism, no active tectonics to make this work. It's a bit of a current thing. Well, not no magnetism, but no tectonics. Where do we get the rare earths from? So there's lots of work. We did lots of work to figure out where we get the rare earths from to make this. And this is probably the best evidence. It's neodymium isotopes. I know not everybody loves isotopes, but this is a pretty simple story here. Essentially, what we're looking at is neodymium isotopes are very useful because you're actually dating the metals, or you're examining the metal of interest, so you need the rare earth. If you have mantle-derived magnets, which you do have pretty much every other rare earth ore deposit, they should sit up here in this grey thing. Okay? Brown's Range, don't worry about that guy there, the light blue. There's samples of Brown's Range for all these colour bars here. They set at about -20, which is very, very crustal white. And in fact, this brown one here is BRM, Brown's Range metamorphics. It's the same signature as the sediment host of the actual mineralization. So the metals themselves, the rare earths, are actually coming from sediments. There's no magnets involved here at all. And that's supported by lots of other geochemical and isotopic data as well. So the general model here is essentially very similar to unconformity uranium system. You have the original unconformity here, you have fluids circulating into that basement. They have to be saline, and the inclusion evidence shows that is. They strip out rare earths from these sediments, and they flow off on these fault zones. We have phosphate-bearing sediments coming up, phosphate-bearing fluids, low pH fluids coming from above where the two mix. They're on this unconformity surface on these faults. You precipitate rare earth phosphates like phosphorus and rare earths. They go together, they precipitate rare earth phosphates. So that's the general model, and there's a bit of a reaction written here, which also explains some of the alteration. The interesting thing about this is actually forming rare earths nowhere near some weird non-point magnet rock. It's in a basinal setting. There's lots and lots of basinal settings like this across the world. All right, so to summarise that, that's coming out a bit funny. But anyway, this is a sort of simple cartoon to try and put this all together. So all of these different ore deposits, they look very different at the surface. They all have quite unique geology, but you can link them to these large-scale faults, structures that either go all the way through the crust or in some cases all the way through the lithosphere. And these are clearly very important for as pathways for melting fluids to come up from below. We have, at least in the case of Tungai, and I think in other cases, offsets in the asthenosphere here. And I think this is really important because this provides a way to have very low degree melting. You want low degree melting because that makes the most rare earth rich magnets of the mantle without any active tectonics, because you can flow that asthenosphere along this edge, you can melt that material, and then that can be channeled up along these faults to undergo crystallization. Brown's Range is sitting over here, that's different things looking at because that's basic. So I think that's these things are pretty useful. You can actually start finding these or looking for more of them. My final point here is a little bit about geochronology and the age of ore deposits. And now that we have these tools to be able to date them, we can start putting this together on an Australian basis and on a global basis. So here's our Australian rare earth ore bodies as a function of age going from today back to 2.8 million years ago. And you can see most of them are sitting in a time window between about 2 and 1 million years ago. Okay? If you look at the global record, which is down here, this is about 150 different ore deposits around the planet. We also see this big peak here sitting in that 2 to 1 million year age, but most of them are young. They're down here under 500 years ago. In green here, this curve here is a cumulative distribution of crust, continental crust, as a function of age. Okay, so what we see, this big peak here is not that surprising given that between 50 and 100, so 50% of exposed continental crust is of that age anyway. So you would naturally expect it to be lots of deposits of that age. If you look at this period here, Proterozoic, that's about 30% of all the world's rare earth ore bodies, including Bainovo, by far the biggest monster rare earth deposit in China, by most of rare earths, plus Mountain Pass, plus Olympic Dam, plus this is Mount Weld out here. So a lot of the biggest rare earth ore deposits sitting here, and the exposed crust across here on the planet is about 10%. So that's not just it's more than a sort of statistical anomaly. That really is a great time through there to make rare earth ore deposits. Previously, people have called this the boring billion because lots of things weren't happening at this time. There are no gold deposits at this age, there are no nickel deposits at this age, there's no porphyries, for example. There's not much going on in terms of global tectonics, and there's not much going on in terms of climate change. But I think those things are actually what you want to make a rare earth deposit in many cases. So I think this is actually, far from boring, it's a really interesting time in the history of mining critical mineral deposits. From the Australian perspective, that's really useful because Proterozoic basins, so this is the mid-Proterozoic, but generally speaking, you can see Proterozoic basins and origins, so the green, so blue and grey here, that's a large percentage of Australia, including a large part of South Australia. So I think there's a lot of potential to find more rare ore bodies in Australia, and I think Australia's got a great future for being provided rare earths. It is already, but into the future as well. Okay, that's it. Thank you.
Do we have any questions for Karl?
Thanks. Rod Hill. It's all well and good to find rare earths, but it's a matter of, is Australia going to be condemned to just exporting a concentrate, or is there capability on shore to produce the high value rare earth amongst themselves?
That's probably a question for politicians. No, I think there is, and I think that the government is actually moving that way. So at the moment, we can't directly compete with China in terms of the price of rare earths. We have our own global market, although Linus is an operating one. I think the key here is that we've got to be, we can't just produce them and send them overseas like we do with most things. We actually have to start bringing together with other raw materials and manufacturing things like batteries and motors. And I think that's actually, at least, it's political talk that politicians are talking about. So I think that's it's become, they're such strategically important metals that we can't keep relying on China. The other thing is, of course, these are hugely important for defence. Modern defence systems cannot operate without rare earths. If China is going to restrict supply, that's a big problem. So I would hopefully say yes, we can, but it'll require smart ways to do it.
Yeah, David Turley here again. He's answered the question well, but it comes back to what he first said of why these things were mined and are mined. It's uranium and thorium. Therefore, it's political in Australia, and we have to deal with the management of UTH to, in fact, even think about rare earths and the position globally on them. It's put up a very good case that we probably have quite a few of them here. How do you actually influence UTH and politicians? The direction is being considered. I'm very glad we have the Royal Commission here with Kevin Scarce, and they are ongoing at a state level and also at federal level. Politicians looking at these things and the downstream, not just of the rare earths and the integration of those with technologies, but also things like uranium and thorium power combined together, and that would be so. That would be a comment.
Follow up, sorry. We successfully, though, managed to get rid of the uranium and thorium out of heavy metal mineral sands, at least a number of them, rich sands, maybe not the Victorian deposits, which are heavily radioactive, but it is possible to get the radionuclides out of these things. But I do wonder, though, the supplementary question was, why mineral sands only 2%? It's already a concentrate. So why aren't they being mined for rare earths much more than monazite, xenotime in them than they are, because they're already concentrated?
Yeah, I don't really know the answer to that.
it seems like an enormous resource. So in Australia, I think it's more about, historically it's been about environmental issues, just the location of stands in Queensland, West Australia, but I don't think that's not the question. I don't really know. I think there's a lot of potential.
Are there any other questions? Anyone want to talk about the boring billions? I don't think it's boring anymore. All right, if we have no further questions, I'd like to invite Dr. Stephen Hill to come up and do the vote of thanks. Stephen was appointed the Chief Scientist of Geoscience Australia in 2018, but he will be well known to all of us here in Adelaide for his former role as the Chief Government Geologist and Director of the Geological Survey of South Australia, and also for his time lecturing at the University of Adelaide. So without further ado, Stephen, please.
Thanks for that, and thanks for the opportunity to be able to come to a face-to-face meeting. Of course, my work is based in Canberra, but since COVID, I've been over here, and it's great to have some people for real. And really on that, I want to build on that and say thank you, Karl, for your presentation today. Indeed, you have been talking about, I love it, you described the most critical of critical minerals, and I know there's been a bit of government political discussion that's gone on here in the questions, and let me assure you that there is no shortage of recognition and discussion in Canberra about critical minerals, rare earths, and where we're going with that, and particularly using that to drive a lot of our strategic relationships with countries like the US. So you're right in the middle of a really important area, and not only those uses that you outlined, it was great to hear you talk about the defence importance, because that is a real thing for all of us. But of course also in South Australia, it's important to think about the value of these elements for space and our ambitions around space, and of course South Australia being central to that. So Karl, I think you've come to a great place geologically, you've come to a great place to work on a strategic commodity, and I hope that you're seeing today that you've come to a place where there's a great resources community. And I think that's a really important thing to share with everyone about people like Karl coming into the South Australian resources community, because if you look around the room here, you can all think about the legacy and impact that you've all either made or are on the verge of making, and to see new people come in, be part of the community, lead that, potentially that change towards that legacy of how we think about our state and its geology, I think is really exciting, Karl, and I just know you're a great person to be part of that, and I look forward to seeing that legacy develop. Just to wrap that up, Mark McGough has trusted me, because I did try to knock it over at one stage during the presentation, but it's still intact. And so really as a token of our appreciation, I'd like to give you this package. Thank you very much.
Thank you, Stephen, and thank you, Karl, and thank you, Ben, and thank you all for attending our first face-to-face for since COVID. Look, I will come to wrap it up just now. Just simply encourage you all to please come to our next event in August. The 20th. It's on Carrapateena. Other than that, please hang around, network, and we'll see you again at our next event. Thank you very much.